Section 7.2 discusses a method for finding eigenvalues. Hopefully you remember something about eigenvalues from matrix algebra. If not, you might want to go back and review chapter 4, and there's some review in the book in section 7.2 about what eigenvalues, eigenvectors are, and the fact that symmetric matrices only have real eigenvalues, but non-symmetric ones could have complex eigenvalues and so forth. In my graduate course, Computational Linear Algebra, we discuss a number of methods for finding eigenvalues that are transformation methods. That is, they take the matrix and multiply on one side by S, on the other side by S inverse. That doesn't change the eigenvalues, and you keep repeating that until you get it down to a form where it's easy to find the eigenvalues, namely diagonal or upper triangular. A diagonal matrix, you can just read the eigenvalues off the diagonal. Upper triangular, also read them off the diagonal, or something close to diagonal or upper triangular. But they're fairly complex methods. The only method we're going to talk about in this section is the power method, and it's extremely simple. All in the world you do is you pick a vector at random. Don't pick the zero vector. Most anything else will work, but not quite anything. Basically just pick a random non-zero vector and start multiplying it by a. That's all there is to it. And eventually Vn plus 1 will be approximately a multiple, scalar multiple of Vn, and that scalar multiple will be your largest eigenvalue. Now, to see why this works, well, first notice that Vn is just a to the nth power times V0, because V1 is a times V0, V2 is a squared times V0, and so forth. Every time, each iteration, you just multiply the previous vector by a. So after n iterations, you've multiplied the original V0 by a n times, so a to the nth power V0 is Vn. Now we're going to assume that a is diagonalizable. If you know from matrix algebra, not all matrices are diagonalizable. And if it's not diagonalizable, the method still works. It's just the proof is much harder. You have to reduce it to Jordan canonical form, and it's a lot messier. So we're going to assume this diagonalizable, which it will be if A is symmetric or has all distinct eigenvalues in lots of other cases. So like I say, the proof is just a lot harder if it's not diagonalizable. So we're going to assume that A is diagonalizable. That means that A is equal to SD S inverse for some matrix S, where D is a diagonal matrix, and D has to have the eigenvalues of A along the diagonal, because the eigenvalues of a diagonal matrix are the diagonal elements, and A and S are similar matrices. That is, you multiply one side by S and the other side by S inverse. Doesn't change the eigenvalues, so A and D have the same eigenvalues. Eigenvalues of D, you just read them along the diagonal. Therefore, those are the eigenvalues of A. And let's assume that lambda 1, we'll just call it lambda 1, the largest eigenvalue in absolute value. And notice we're assuming there is one eigenvalue that's larger than all the others. If it's a tie for largest, you've got a problem. For example, if the largest eigenvalue is 3 plus or minus 4i, those are two different eigenvalues with the same absolute value, and A won't work. The power method won't work for that. Or if 10 and minus 10 are the largest eigenvalues, that won't work. But if 10 is a double eigenvalue, that's okay. So anyway, we're starting from assuming that A is SD S inverse, where D is diagonal matrix. Now, we're not assuming we know D or S. If we knew D and S, we'd already know the eigenvalues and we wouldn't need this method, but we're just assuming that they exist. So what is A to the nth power? Well, A is SDS inverse, and since matrix multiplication is not commutative, you can't just switch the S and D and cancel the S and S inverse, of course. Then A would be equal to D. But A to the nth power is SDS inverse times SDS inverse times SDS inverse n times. And the S inverses and S's cancel except for the first and last, and you get ND's, so you get SD to the nth power S inverse. Now we look at D to the nth power. Remember, D is a diagonal matrix, so it's easy to take nth powers of D. A general matrix, it's hard to find the nth power of A, but the nth power of D is easy. That's just you just take the nth power of all the diagonal elements. And then we divide by the largest eigenvalue to the nth power, And what do you get? Well, d to the nth is lambda 1 to the n. Now, notice we're assuming there may be, lambda 1 may be a repeated eigenvalue here. It's bigger than all the others, but it might be a double eigenvalue. And then lambda 2 is smaller in absolute value. These might even be complex, but smaller in absolute, complex absolute value. So that's d to the nth power is lambda 1 to the n, blah, 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 lambda 1 to the n, lambda 2 to the n, lambda 3 to the n, blah, blah, blah. You divide by the scalar lambda 1 to the n, and these all just become 1, 1, and lambda 2 over lambda 1. Since lambda 2 is smaller than lambda 1 in absolute value, whether the complex or not, you raise it to the nth power and it goes to 0. So if you take the limit as n goes to infinity of d to the nth power lambda 1 to the n, it converges to a diagonal matrix, a constant diagonal matrix, which we're going to call E, which is, it's normally just going to have 1, 1, and all the rest 0, but if lambda 1 is a double eigenvalue, there'd be a couple of 1s there and the rest zeros and so forth. But it's not a, it's nearly 0, but it's not the 0 matrix. Well, then a to the nth power is just s d to the nth s inverse. So limit of a to the n over lambda 1 to the n, you just have a, instead of an e, you have a s on the left-hand side and an s inverse on the right-hand side. So limit of a to the nth power over lambda 1 to the n is just s e s inverse, which is some matrix we'll call G. And the important thing is G is not the 0 matrix. It might be close to it, but it's not 0. But why? Because we know E is not the 0 matrix, and S is invertible, therefore G can't be the 0 matrix, otherwise E would be. So the limit of a to the nth power, that means a times a n times, over lambda 1 to the nth power, is some non-zero matrix, assuming there is one eigenvalue larger than all the others, and we're going to call it lambda 1. Okay, so if a to the nth power over lambda 1 to the n converges to some fixed non-zero matrix, that means for large n, a to the nth power lambda 1 to the n is almost the same as a to the n plus 1 power over lambda 1 to the n plus 1. You know, a to the million over lambda 1 to the million is the same as a to the million and 1 over lambda 1 to the million and 1 power, because they're both equal to g almost. And from that, you multiply both sides by lambda 1 to the n plus first power, and you get a to the n plus first power is approximately equal to lambda 1 a to the n. So that says if you just took the matrix A and started multiplying by A, and you get a squared, a cubed, so forth, eventually, after enough iterations, each time you multiply by A, you just get a scalar multiple of the previous matrix, and that scalar multiple will be your largest eigenvalue. And in fact, you could do the power method that way. It would work, but the problem with this is that every iteration now you're multiplying two matrices, which is in cubed operations. We prefer to multiply both sides on the right by this V0, your initial power method non-zero vector. And then you see this is just Vn plus 1. You know, V0 multiplied by An plus 1 times is every time you multiply you get another V. So after n plus 1, multiply by An plus 1 times, you got Vn plus 1. Multiply by n, you got Vn. So now if you take V0 and start multiplying it by A, eventually you get Vn plus 1 is approximately lambda 1 times Vn. And that, so each new vector is scalar multiple of the previous one. The scalar multiple is your largest eigenvalue. So you could actually do it this way, but that's, or it's in cube work each iteration because you have to multiply matrices every time. But here you're only multiplying vector times a matrix, which is in square work. So that shows that if you take a random non-zero V0, start multiplying it by A over and over, eventually what happens, eventually each new vector is a scalar multiple of the previous vector, and that scalar multiple is your largest eigenvalue in absolute value. And by the way, Vn is the eigenvector corresponding to it, because notice that A times Vn, so Vn plus 1 is just AVn. So if Vn plus 1 is just lambda times Vn, then that shows that A times Vn is lambda 1 Vn. So not only is the scalar multiple the largest eigenvalue, but the Vn is the corresponding eigenvector. So is Vn plus 1. And by the way, notice that the speed of convergence depends on the ratio of the second largest to the largest. If the largest eigenvalue is 10 and the next largest is 9.9 or minus 9.9, then this goes to 0, but very slowly. If they're 10 and minus 10, it'll be minus 1 to the end. It won't go to 0 at all. But if it's so you have to have one eigenvalue that's bigger than all the others, even if it's multiple eigenvalue. But if you have if your second largest is almost as large as the largest, then this will be nearly 1 and it'll go to 0, but slowly. So if your second largest eigenvalue is much smaller than the largest, then it'll converge faster. So the power method finds the largest eigenvalue, and the more it stands out above the others, the faster you'll find it. In your homework, you'll have a problem, two problems where one, the eigenvalues are neck and neck and it converges real slowly. So power method couldn't be much simpler. You just take a random non-zero vector, start multiplying it by a, and eventually each vector will be a scalar multiple of the previous one, and that scalar multiple will be the eigenvalue, largest eigenvalue of a, and the vector will be the corresponding eigenvector. Remember, the eigenvectors are not unique. You can have any eigenvector multiplied by any non-zero scalar, it's still an eigenvector. So Vn plus 1 and Vn are both approximately eigenvectors, even though this one is lambda 1 times larger. It's not unique. You can divide by the magnitude and get a normalized eigenvector is what we're going to do actually. Well, an obvious problem with the power method, it's really simple, but it only finds the largest eigenvalue. What if you want, well, if you want all the eigenvalues, you probably shouldn't use the power method. You should use one of the transformation methods that find all of them, but they're more complicated. But you can find other eigenvalues other than the largest one, and you do it with a little trick called the shifted inverse power method. And the iteration now, again, you choose V0 at random, and then you basically try to find the largest eigenvalue of A minus Pi inverse. Let's say you're trying to find the eigenvalue closest to P. So if you want the smallest one, choose P to be 0. You can go fishing for the eigenvalue closest to P. You pick a number P and we'll find the eigenvalue of A closest to P. How do we do that? We take the matrix A minus Pi inverse and keep multiplying V0 by that, and we'll find the largest eigenvalue of this matrix, A minus Pi inverse. And by the way, you don't normally fool with inverses here. It's more efficient to just solve this system every time step rather than find an inverse, but you could do this way. Anyway, either way, you're basically finding the largest eigenvalue of this matrix, and you know, that's what the power method does. It finds the largest eigenvalue of whatever matrix you're multiplying by. So eventually Vn plus 1 is a scalar multiple of Vn, but that scalar multiple is the largest eigenvalue in absolute value, not of A, but of A minus Pi inverse. And the eigenvalues of A minus Pi inverse are 1 over lambda minus P. So the largest one of those is 1 over lambda P minus P, where lambda P is the one closest to P. That makes the denominator smallest. So the largest eigenvalue of this matrix will be 1 over lambda minus P, where lambda is the eigenvalue of A closest to P. And that's the one the power method will actually find. That's the largest eigenvalue of that. So once you found that, you solve for lambda P, and it's P plus 1 over mu sub P, and you found the eigenvalue of A closest to a user-chosen number P. Okay, let's try the power method out on this matrix here. It's a 3 by 3 matrix. This is actually problem 3 in your book. And we're going to start with 1, 1, 1. And all we do is just keep multiplying x by A. x0 is 1, 1, 1. Each iteration we multiply by A. And now we want to compare the new, this would be like your Vn plus 1 and your Vn. So eventually Vn plus 1, y, will be a scalar multiple of x, but you can't divide vectors, so how do you determine the scalar multiple? And if you do it by hand, you can just look at it and compare the ratios. But one way to do this on the computer is just take the dot product of x with y over dot product of x with x, and if y is just a scalar multiple of x, then this will just give you your scalar multiple. So if y is a multiple of x, this will just be that multiple times, x dotted with x over x dotted with x, which is 1. So we'll print out this is basically a way of getting the ratio of y to x if y is a scalar multiple of x. Now here I set x equal to y divided by the norm of y, because otherwise, I mean, if I remove this line, it'll still work, but x will, well, I have to say x equals y to start over, but it'll still work, but x, if lambda is large, x will get larger and larger until it might overflow, or if lambda is small, it'll get smaller and smaller until it overflows. This way we normalize at each step and start from a vector of length 1 and multiply it by a and compare y to x and so forth. And at the end I use the MATLAB function to calculate the eigenvalues of a just to check my answer. So let's run this. And there's the 3 by 3 matrix. We start with 1, 1, 1. And you can see the eigenvalue is converging to 4. After 7 iterations, it's almost exactly 4. And there's your normalized eigenvector. That's the the Vn plus 1 divided by the norm of Vn plus 1. So sum of squares should be 1 here. And then the MATLAB eigenvalue function tells us the eigenvalues are 1, 2, and 4. And see, we found the largest one, which is 4. So this won't work if the largest eigenvalue is complex, but unless you use complex arithmetic, because then it'll be tie for largest, but you couldn't expect a power method with real numbers to give a complex eigenvalue, but it'll find the largest one if it's real. The others could be complex as long as the largest one's not complex and not tied for largest. So if the largest was 4 and minus 4, it would oscillate back and forth forever. It couldn't decide which to converge to. If it were 4 and 3.9 or minus 3.9, it would converge to 4, but slowly, because it'd have a hard time getting away from the 3.9. Okay, this is the problem I just did. That matrix, you're supposed to apply the power method to a couple of matrices, one of which the eigenvalues, the largest eigenvalue is just barely larger than the other, second largest, so it converges slowly. That's problem 16. And I believe you're also supposed to find the eigenvalues of this 4 by 4 matrix using the power method.